about two new C++ 17 features has include and inline variables. So actually, both of them are something that I encountered during my day job in Qualcomm, and specifically this one, and also the inline variables is inspired by the C++ 17 in details that I showed in previous slides. So let's start. So let's say your code has to work under many different compilers and platforms, and if you had this opportunity to work with many compilers and many platforms, it's not an easy thing because of many reasons. One of the reasons is that different compilers and platforms, they might have different headers that you might be able to include in one but not in the other, and you want to discover that. So C++ 17 gives you another way to kind of discover if a specific platform has a file, has an include, and it's a preprocessor new element that is added to C++ 17, and it's basically you can use it in pound if underscore has underscore include, and then you provide the header name. And at the end of this slide deck, I'll show a couple of slides of what I needed to do, because in a recent work I needed to work on Android, like a C++ 17 app that needed to work on Android with the NDK, on Ubuntu, WSL, which is Windows, and Cygwin, which is also Windows. And it's really a pain to get everything working. It is working well and all, but it takes time to get everything working in a consistent manner. So first of all, it's available in Clang as an extension for many years, but now it's added to the standard. It's probably not the first time that something like this happened. It allows you to check if a particular C++ feature or header is available. And when I say feature, for example, in my case, I needed to test if a file system header exists, or maybe it's in a different location and things like that. The nice thing about it that if you have a C++ 17 compiler that supports this macro, this macro is going to be available even if you pass C++ 11 as an argument to the -std option to your compiler, which is really nice. You can actually work on C++ 11, and as long as you're having a C++ 17 compliant compiler, you can still use it, which is really nice. And I'll show. I try to kind of see which compilers between GCC and Clang, which versions start supported. And I'll show it in one of the slides, like the versions that I discovered. So here's an example. So let's say char conversion header that was declared as C++ 17 low-level conversion routines. So so first of all, you want to know if has include is defined, and if it is defined, then you can check if char conversion is there in the platform. If it does, you can define some stuff, include some stuff. You can do whatever you want, and I'll show you what I needed to do. At least worked for me. But the sky is the limit. You can do whatever you want in this block. So in this case, the author decided that it would define has char conv as 1 and include it, and then if the has char conv is defined, you can use from chars, which is a new standard C++ 17 function. Otherwise, you have your own alternative implementation. It's a very straightforward solution. So yeah, this is basically explains what actually happens, and you can play with this specific code in GCC 7 dot something or 9 dot something, and you can see that in 7 dot something it doesn't have the char conf, so you need to have your own implementation if you want to kind of an alternative one to chars. So one thing to note, this is something that I realized while I was reading that and investigating. You can really have this if like pound if defined and then end if has include. It wouldn't compile. Like you cannot put it in the same line, so be careful with that. You'll get a compilation error. I actually tried it out. Uh, Apparently, if has include underscore has include is not defined, this whole expression is wrong. So the preprocessor would say, because it needs to kind of evaluate or maybe parse both of them, not evaluate, but parse both of them, and you need to separate it into different lines. So be aware of that. So Clang, actually, I tried all kind of versions in godbolt.org, which is the compiler exploit that I used before to show you the code. In GCC, 492 and above worked fine. So from 492 has include worked fine for me. So one of the things that you need to be aware that, okay, sometimes you check that the header is included, but in early implementation, there might be just a stub, header stub that is, and it might be empty or not, the function are not implemented. So be aware of that. There is some wrinkle here that you might detect as a positive for a specific header, but you'll find out that it doesn't actually implement everything you need, or maybe some of the function are kind of empty or does not exist. So be aware of that. And this is like for this charconf C++ 14 will have wrong results, for example. So I realized that in 20 they've been added more elements that can be, you can actually test for a specific, a more granular kind of C++ feature parts. For example, do you want to test if stud any exists? So there is a cpp underscore cpp underscore lib underscore any. By the way, everything that starts with underscore, especially underscore, it's kind of reserved. Don't use underscores, prefix underscores. Don't use leading. Postfix is fine. Same deal for lambda and all of that. So this is, and I have a link here for CPP reference. You can actually take a look at all the new elements that have been added in order to discover all kinds of C++ features. So yeah, it's at the bottom line. It's really simplifying. Like it's a step forward. Obviously, the writing for multi-platform is tough. Even when I write against POSIX platforms, there is a lot of differences between the platforms. If you had a chance to write with POSIX for multiple platforms, you know what I'm talking about. But it's just another way to kind of ease the pain of working on multi-platforms. And again, I worked on Ubuntu WSL 1.0 and NDK, and which is Android, and Cygwin. So it took a lot of effort to get everything, everyone happy. So my personal experience is I worked on Ubuntu, which had 9.x GCC, and we needed to make it work under WSL 1.0 Windows version 10. and it has 7.x. So WSL, it's the Windows subsystem Linux. I personally really like it. Looking forward to start using 2.0. I heard that it's much better and faster. But the problem is that the 7.x GCC had file system, std file system that is under experimental namespace and experimental subfolder. So that basically needed some treatment. So what I did is if it was if the has include was defined, and it was defined for 7.x and 9.x, and if you have file system included, then I'll include file system, and then my file system would be std, and then so my namespace, that is, it would be std, and then if otherwise I'll use experimental file system. Obviously there are other options, but that worked for me pretty well, and my file system namespace alias would be std experimental. So this is basically how I solved that, and it worked pretty nice for me. So that's hopefully something that you can take and use it in your if you get into this issue on multi-platforms. Any questions before we move to the C++ inline variables?
Kobe, it's a little bit off topic, but I'm wondering, do you know of any tools that would take a snippet of code and just compile it with every compiler in various versions? Kind of along the lines of Godbolt.
Like automatically?
Yeah, yeah.
I'm not aware of. We can check it.
Okay, thank you.
Okay. Just making a note. Okay, so let's move to the inline variables. Again, it's a C++ 17 feature that would be very useful in many cases where you deal with headers, and I'll explain. And this is inspired by two books. One of them I just mentioned, C++ 16 Details, and the other one is C++ 17 The Complete Guide by Nikolai Justice, which is, some of you probably know him. He writes a lot of books. He has many talks in CPPCon and in other conferences. He writes at least few books which are basically the Bible of templates, and I highly recommend watching his talks and reading his books. It's he's a very good speaker and a very good writer. Okay, so when you have a non-static member initialization in C++ 11, you can actually take a look at this integer. You can actually you don't need to have a constructor that. Yeah, any question? So yeah, you don't need to have a constructor that says, user age _0. You can basically skip this whole thing and have these curly braces 0 and this, and for std string you can have this std string name, and this is actually a mistake, and they should have a postfix _, not a prefix _. And this is pretty cool. It saves a lot of typing. There is, in this specific example, if you basically thinking about, is there a constructor? So yeah, there is a constructor that actually is implemented generated by the compiler that initialize age with 0 and name with unknown. So there is something like this happening under the hood, but it's pretty clean. You can see that it's really nice, and I'm using it a lot. Like, this is my default. But the thing is, with static variables or constatic, you need a declaration and then add definition in some implementation file. Now I'm going to repeat that, but I'm going to make it upfront right now. The C++ 11 constexpr keyword allows you to declare and define static variables in one place. It is limited to constant expression only. So constexpr defined like this, and we'll have examples, you can't really modify it, right? This is a constant that you can't really modify later. But it is something, especially in C++ 17, it has both the definition and the declaration. Okay, so previously only methods of function could be specified as inline, right? So if you think about functions, methods, they could be like function would be like non-member functions, or methods would be a member functions. They could be inline. But now we can do the same with variables, and this is kind of a quote from the proposal that went into the standard in C++ 17. And again, throughout this slide deck, you'd see that it's pretty useful for header-only libraries when they don't want to have a CPP and all of that. It makes life much easier. And I'll show, so I'll talk about motivation, kind of the workaround before C++ 17, and then how C++ 17 makes life much easier and shorter and all good. So if you try to initialize a non-const static member inside the class, you cannot do this. So this would have a compile time error. Defining it in the same header but outside would have a link error, especially if not especially when it's included in multiple CPP. So you can be fine if it's just one, but the moment you have more than one, you'll have a link error because you have multiple definitions happening here. And basically, this comes from the one definition rule that a variable or an entity has to be defined in exactly one translation unit unless the variable or the entity is declared to be inline. And we'll see what does it mean. And you can say, hey, Kobe, what about include guards? So include guards doesn't help because include guards are per compilation unit, right? But if I have multiple compilation units, including the same one, include guards would not help you. So it's not like the header might be included multiple times in the same translation units. The problem is two different CPP, two different translation units, including the header. And then we'll get multiple definitions when the linker kicks in. And it's a common issue for header-only libraries. And there are many, it's kind of a trend that we have right now. I don't know if right now, but it's been like this for some time, that people like to have a header-only libraries, and GitHub is full of such examples. When you just, and it's really appealing, right? You just drop it in your project and you include, and you're done. You don't need to compile, don't need to, and you don't need to have, like, if you have multiple platforms, you don't need to compile to each platform. This library you just include, and I'm using let's say JSON parsers that are header only, and it makes my life very easy. So that's one thing. Okay, so what are the workarounds pre-17 that we had today? So first of all, in some cases like integral and enumeration types, you can do it, and usually I tend to forget, like, I try to write and initialize, and then the compiler or the linker would tell me, look, this is wrong, and oh yeah, right, I cannot do this. I need something else. So it's allowed for literal types such as fundamental, integral, floating points, pointer types. There are some classes with only constant expression to initialize a non-static data, and they need to have no user-defined or virtual destruction. So there are all kinds of restrictions. But in some cases, static const would work with some of the types. If you need to take a reference of this specific instance, then you'll have some issue. If you need to bind it into a reference, and I have example in one of the slides. So what is the workaround? So some would have like an inline function that in this case just returns a string, and the string is static. So what happens in C++ 11 and beyond? First of all, this is a thread safe since C++ 11. So that's one thing. The second thing, as we know, this is not a C++ 11. It's going to be initialized when we enter the function. Sometimes it's not that good because sometimes you want to initialize stuff not like this, not like what we call on demand. We just want to initialize it at the beginning of the executable and not when you're actually calling this function. So this is a throwback. And this is a non-member function. You can do the same with a member function. So this is one simple workaround when you need to initialize some static type, string in this case. C++ 14 added this variable templates, and this actually works well because templates, when they are just like you think about a template function, when you have it in a header, you don't need to. It's basically kind of the linker would do the right thing, right? You don't even need to have inline added to the function, and you still can include it for multiple translation unit, and it's working. It's the same idea here. So it's a workaround since C++ 14, and another workaround is that I can have a template class, and I can have a default template parameter, just a dummy one. And this is really ugly, but this is just a possible workaround. Sorry? Okay, I thought there was a question. So this is another usage. And again, it is ugly. Obviously, there's a lot of code added, and you can even inherit that. Obviously, this whole thing, there's a significant overhead. It's less readable. There is mental overhead that you need to understand. Why are you actually doing all of these? You just need to initialize something, and you go and define a member, or maybe define a template when it shouldn't be a template. So it is a significant overhead, and fortunately we have a solution that was added to C++ 17. Yeah, the last part, the initialization of global variable might be postponed until its first use. For example, when you have this static function, only when you call this static function, then the initialization kicks in. And sometimes you don't want that. You want the initialization happens when the program starts. Okay, so how do we do it with C++ 17? It's pretty simple. So this is just the kind of the overall idea. So we have a static inline of size t, counter equals 0. It's not const in this example. That's fine, and this works well. Again, this for size t, you could have it without inline because it's an integral type. But for other things, and I'll show more, that inline helps us. You could also, the following is also a valid syntax if you want to just have static const or something like that integer in the declared in the class, but defined later in the same header file as inline. This is also fine. You can include the same header for multiple compilation units, and the linker would be happy and not going to complain on anything. And of course, you can have everything in the same location. And it's something that I'm going to repeat. constexpr, they are implicitly inline, so you don't need to say constexpr inline my var equal 10. This is the inline is redundant here. Now with inline, you have you can have a single global object, which is pretty cool. So take a look at this example. There are two things here. One, std string message, okay, is inline, static inline, all good. It's the same message for all the instances of my class, but I can actually have a global. Don't do a lot of globals, of course. The globals are kind of harmful, but this is an example. If you still want to have something like this, of my class, and this is a new thing. It wasn't available before CPAPA 17. It's okay even if included by multiple CPP files. We'll have only one my global object, which is a great thing if you think about it, because we didn't have something like this, and sometimes it is needed. There are some global things like loggers and still things that you might want to have. I've seen a lot of loggers. There's one single global logger, and this is a good example how you can actually create one global with the inline keyword. So how this basically simplify the code? Think about before CPAPA 17, if I wanted to have some seed that being set by some function, I need to have this function seed, call rand, get the value and return that. But this is now simplified into a single line in CPAPA 17. You can have static inline int seed equal rand, and we have the seed, and that's it. The nice thing CPAPA 17 guarantees that seed will have the same value. It's computed once, and it's the same value across all compilation units. So the inline used here as the same semantic as function declared inline. What does it mean? And this is something that kind of the official form of what is inline. It can be defined in multiple translation units, provided all definitions are identical. So there is one definition identical for everything in multiple translation units. Or it must be defined in every translation unit in which it is being used. So these two things basically are the same as what we have right now with variable inlines. So by including the definition from the same header file, this is what we have with inline variable. So the resulting behavior is as if we had exactly one variable across all compilation units, which is pretty cool. And you can do it for any namespace. It can be global or any namespace. You can have it for atomic. For example, if I have a single atomic that needs to be the same for all, like the same instance for all compilation units, and I include it in the header, we couldn't do it before that. So adding inline would do the trick for you. And yeah, you need to initialize stud atomic when you define them, so you can do it in one shot with the inline solution. You still need to make sure that types are complete. So when I have this struct my type, and I have and I'm having this inline, the same header, I have in inline my type max and some value here. Since my type is already a complete type by the time I'm actually having this I would say let's say a global static my type. So this code is fine. If so I need to have, like compiler has visibility, should have visibility to the complete type. So no forward declaration or anything like this. So how about constexpr? Like how that would differ from constexpr? They are more flexible. So if you use inline variables, they are more flexible because you can actually change them, and you don't need to initialize them with a constant expression. So for example, I can have I can use rand, like any other function that will initialize my inline variable. This is not possible with constexpr unless I'm initializing it with a constexpr function, and that would be fine. But if a specific function is not constexpr, this would not work. So I cannot use it with constexpr. For static data members, constexpr now implies inline since CPAPA 17. So having static constexpr int n, it's a declaration with 11 and 14, but it's since 17 is also a definition. It's as if you had inline, you stick inline at the beginning of that. You don't need to. It's already done for you in CPAPA 17. And the nice part is, so before CPAPA 17, you could have the declaration only without a corresponding definition. So if you have this n equal 5, it's fine not to have definition. We use it, we pass it by value, I would say. We don't take the address of the : n. So that would work. But the moment I actually want to take a reference or bind it to a reference, then this part would not work before CPAPA 17. And same deal if I want to just take the address to assign it to const int pointer, it wouldn't work without a definition. But again, CPAPA 17 solve it for us. constexpr is both definition and declaration, and you're done. You don't need to do so. You again, you get away with before CPAPA 17 with this code not having definition, as long as you don't need to take the address of n. And usually, what I'm seeing in code that use constexpr, you just want it. It's like pound define, but just better, much better. Don't use pound define. Use constexpr, obviously, because macros, they don't care about namespaces and all of this stuff. They don't care about it. It's like search and replace kind of a thing. constexpr and other elements, they conform to the syntax of the standard, and they are aware of, oh, I'm in this scope, and it's much better in terms of not having surprises. Don't use macros unless like you have no other choice. And usually, if I want to repeat something, just like the example that someone asked about float 16, kind of might be a good example. So yeah, I just talked about it. So this, for CPAPA 17, you're good. It's declaration and definition. Thread local storage. It's another thing that we get from that. We can have inline static thread local. Thread local is something that was added in the standard from CPAPA 11. So we can have a good way to use a TLS or TSS, or there's all kinds of names. It's the same thing, thread local storage, but in a portable way. And I can have a unique name per thread, and the same deal for the bottom expression. So it's very, very useful because each thread would get its own instance. By using this inline, we'll have no issues with linker issues and things like that. So actually, we have 25 minutes. Any questions? Because I think I have 20 minutes to show you some stuff about ranges. If you want me to, I can go ahead. It's pretty interesting stuff. Okay, so let's do it. I'm going to use Compiler Explorer, and so let me just. This is I'll say this. This is a CPAPA 20 cutting edge type of features. I am in the process of learning CPAPA 20. It's something like double the standard, and it's not straightforward to learn. There are core routines that you can probably know from C#, Python, generators, and other languages that they have something like coroutines. There are ranges, stud format, modules, concepts. There are lots of things that being added to the standard. There's a lot of things to learn, and for specifically for ranges, it came from ranges v3, Eric Nimbler. You can go to his GitHub, and actually there is a library here. You can actually ranges v3 should be somewhere here. Here, ranges v3. So you can actually play with ranges v3. I'm going to use the ranges that is provided by GCC 10.1. I couldn't find it working in the Clang trunk at least a couple of weeks ago. So let's see how this thing can improve our code. So it's gonna be interactive, and you can ask questions if you want to. So I'm going to create a vector of stud strings. And some of the people from Qualcomm maybe already saw that, so might be looking familiar. And I'm going to provide some strings to like AA, and then okay, that should be enough. And let's say I want to count for each element in the vector. I want to count how many strings we have, and there are multiple ways to do it, obviously. So I'm going to have a count. Actually, what's the results? And I'll make a function named count. I'm going to pass a vector. Okay, so let's. I'm going to show all kinds of other elements. So no discard. So I'm not forgetting to have to obtain the results from the return value, that is. Stud vector would be what I'm going to return. And count. And I'm going to get const stud vector stud string by ref, call it v. Okay, so again, multiple ways to do that. This is just one traditional way. We'll have stud vector of, because we want to provide, it can be integer or unsigned, doesn't matter for this purpose. We want to provide a vector that has each element would tell me how many characters, like the string length of each of them, each of the members of the vector, the incoming vector. So results. So I'm gonna kind of prime it with the size of this vector, the incoming vector. Otherwise, I need to do push like a back inserter, but I can do lots of stuff. So just for convenient, I'm going to have a lambda. Make it const. I'm gonna make it count chars. And okay, so the lambda would do this. So this is the capturing part. This is the parameters, and this would be the body of the lambda. So I'm going to make it const auto by reference s. I know it's the incoming are strings, so I'm going to make it by reference, and then I'm going to return the size of it. And I don't need to capture anything. Okay, so remember we talked about taking a specific range and convert it to a different range. So you already know that stud transform is something that is a good candidate to use. So stud transform, and I'm going to str begin And I need to probably have algorithms. So begin and end. And so this is the range. And then what would be my output container? I need to provide an iterator. So I'm going to do results.begin. And again, if I didn't have it primed with the side, I'll just make stud back inserter. It's the same thing for me. And then how do I mutate the elements to be able to be into to insert before we insert to the output iterator? So I'm providing the count char lambda, and I'm going to return that. Okay, so if I didn't have any typos, I should be able to use a for loop, like a range for loop that was introduced in 11. Basically, I don't need to have reference here. I just can, because it's basically integers results. And I'm going to do stud clog of result. I'm just gonna make I need IO stream. And I have a typo here that I can see. I actually want to return an integer, a vector of integers. Okay, let's let it compile. So 2, 5, 2, and 1. It does the right thing. So let's now try to see how we can make the same thing with ranges. So I'm going to include ranges. And I'm going to use the same vector, but I'm going to have a different function. Okay, so const auto, I'll call it results ranges, just to have a different name. And I'll call it ranges count. This will be the function. I'm going to pass the same vector. Again, the vector is count. We didn't mutate it. We just use it to create a new vector. So no discard. Same thing. We'll have stud vector. By the way, I could make it auto as a return type. Could be fine, I think. So I call it count, ranges count. So ranges count. And the same deal. I'm going to have a stud vector of stud string, the reference of that one strings. And now I'm going to use the same lambda. So I'm going to make a copy of this. Okay, same lambda, and now what I'm going to do is I'm going to return. Return the strings, and I'm going to. This is basically like I have all view on the strings, and then I pipe it to stud views transform of, and I need to give the mapping function, and the mapping function would be I call it count C. So it should compile without any issues. Let's see. Let it compile. Oh yeah, this is my mistake. I'm kind of was copy paste from the previous. So actually, the return type is not really a vector int. It's actually it's an iterator. Remember what I told you? It's an iterator that is being used in the full loop that I'm going to write in a second. So I could figure out what the type is, but I was lazy and just put auto. and the magic happened. The compiler is figuring out the type for me, and all is good. So I forgot, I looked at the generated code to see the actual iterator that's being, it's a view on this transform. And as I mentioned, it's a lazy evaluation. Nothing actually happened here. I just got a pointer or an iterator to something that once I start doing, I'm gonna run some stuff, then things would start working. So I'm going to do, actually I'm going to do the same thing. I'm going to take this one, paste it here. But, I'm going to use the ranges.
6 minus 7 minus.
Okay, so we got the same one, 2, 5, 2, 1. So obviously, at least for me, once you get used to the functional programming style and this pipeline style, it's definitely a better approach. Let's see what else can we do. We have 10 minutes, exactly what I need for the couple more examples. So, and then, by the way, there are many of them, and ranges v3 is kind of different from what's being part of the standard. So if you look at v3, you'll see maybe different namespaces and different capabilities. Okay, so I'm going to have vec1. I'm going to initialize it with 1, 2, 3, 4, and 5, and 6. Okay, so let it compile. I have a question here. Take a look at this code. It compiled without me actually specifying that this is a vector of integers. So stud vector is a template, but I didn't need to specify the template parameter. So this is a feature in 17 where the compiler can deduce the template argument. So if I'm not mistaken, this is a CTAD, where if I put 6.0, this would be an issue because the compiler would see, oh, I have double and I have integers, so what would be the type? But since all of them are integers, the compiler says, oh, I have actually an integer. There's a constructor, or we can talk about it in future meetups. There is a syntax to teach the compiler to deduce the right template parameter. So this is an example. I just gonna show you this example because it's pretty nice. Okay, so let's say I want to have a view, and I take vector1, and I want to have a view, but I want to look at the reverse part of the vector. So I want to take a look at it from reverse, from 6. And then let's say I want to drop 2 elements. So I'm looking at 6. I want to redrop 6 and 5, and I want to take a look at 4. So if I do clog of so v is an iterator. So think about begin, and I'm going to dereference it. So I should be seeing 4 if I didn't have any typos. Did I have any typos? Let's see. Yes, we see 4 here. Okay, so this is pretty cool because and again, it's all lazy evaluation. It's pretty nice. Okay, let's take another example. So again, we have stud vector. I'll do the same trick. So we're gonna call it vec2. So I'm not specifying anything. I'm gonna do 0, 0, 1, 2, 3, 4, 5. So let's show how we can do it with in a for loop. So auto n or whatever you want to do, and then I want to take a look at the entire vector. I want to have a view on the entire vector, and then I want to take just 2. And I can print it. I'm gonna copy this, paste it here, and I'm gonna do n. So if I didn't have any typos, this should be giving me 0 and 1 because I just wanted 2. This is another nice thing. Let's have another one. We have another 6 minutes.
Kobe, can I ask a quick question?
Sure.
On line 37, you have standard views reverse. What is the data type of that? Is that a
so again, I'm not an expert. You get an iterator to it's basically a view. If we could, let me see if CPP Insight can help us. Let's see. So the Compiler Explorer has this nice feature. I tell you what, CPP Insight would not help us because CPP Insight is based on Clang, so they don't know yet what is ranges. So this is why I actually needed to look at the binary and see what is the stuff that are generated. So it wasn't straightforward for me to understand what is generated. Maybe you know what? Maybe we can see in sometimes it's annotated. No, I don't see. I needed actually to do like a small research about. Actually, what I did, it's probably not the best thing, but I actually created a compiler error. Maybe there's other ways to do it, and I looked at what the compiler is actually saying, and then I realized what is the type. That is being okay. This is going to be a huge compilation error, but let me see, because it's going to tell us what is the type that we actually were trying to use. I know it's very dumb way to kind of understand, but I'm really learning ranges. Let me see. Oh, okay. So you see this one, stood ranges, drop view, begin, requires. So this is a concept. There's a concept here on C++ 20, random access. So basically there is a class that exposes an iterator. It's an iterator. It has this begin. Obviously, I cannot C-log this one. I need to dereference it. But basically, I know it's dumb, but this is the only way I could. At least CPP Insight can provide me more help in determining what's the type that is generated. But it's basically a collection of iterators.
Okay.
The way I understand that. By the way, there is a C++ functional programming book. This one actually has one of the best books that I've read in C++, and we had it in one of the previous meeting. Take a look at that. It has a lot of information about stood ranges v3, like real examples. This is, I think I had it like a year ago when it was still when Ivan was still writing the book. I had like an early access, and I start learning these ranges, and he explains very well about this whole lazy evaluation and all of that. It's a very useful thing.
Okay, thank you. This is great.
Okay, so let me see, going back here. So let's do the one last example, and we can all go home. I know we already at home, but you see what I'm saying. Okay, so const stud vector ints, and I'm gonna do 0, 1, 2, 3, and const auto even. So even would be gonna have a lambda that has const in I, and I'm going to return 0 equal I modulo 2. That's one of them. And let's square it also. Square would be another lambda that again has a const int I, and we're going to return just I star I. Okay, and let's have a for loop. So auto or int doesn't matter. So I take ints, include views transform. Sorry. Before transform, I want to filter that. So you can probably know from other languages there's this filter. So I want just the even one, and then I would like to have stud transform of square, and I'm going to do stud clog of I, and basically that's it. That's about it. So this is another nice way where you can okay, let's make this guy happy. So it's another way to did I have any typo in the square? Yes, I need views. It's under views. Let it compile, and then we'll see that we'll take the even ones. It's going to have 0, 4, and 16. Yeah. So this is the next gen of C++. This is C++ 20. This is really bleeding edge. When I say bleeding, it is bleeding because there's so many things to learn. If you go to CPP-ref and you look at stud ranges, this is the library is here. Multiple things here to and there's a lot to learn. By the way, you need to understand lifetime. For example, a view is pointing to some existing instance. You need to make sure that this instance lives. It's not like the view because it doesn't make any copy. It's like just like I mentioned in the beginning. It's a string view, so it's like string view. It's like you have a view. The view on the element needs to live while we actually looking at it, and it's all lazy evaluation. So so to keep that in mind. I've actually tried to do something with temporary, and I had undefined behavior and didn't realize it until I learned that view is actually need to have the object alive, the whole thing, and I kind of missed that. So FYI. I think this is it for this time. Thank you for sticking in. We started with I think 90 something. We have 35 now. Please do approach me if you want to present something. As you probably notice, it's pretty simple. I'd be more than happy to help you, and I need you so so other people can present, and if you present, present a specific topic, you learn to be more familiar with this topic. So I highly encourage you to do this. Any questions? No? Okay. Thanks again for
Thank you, Kobe.
showing up. Thanks. Take care.
Thank you.
Thank you.
Good night. Bye-bye.
Very much.
Bye.
Thank you, Kobe.
Thank you.